SwayamPrabha. Digital India. Educated India.
All right, so good morning. I think we can start, and if some people come later, it's no problem. So this is day 3 of our lecture series, and we were basically stopping in the basic introduction to diffusion in the solid state. And so we maybe go back a little bit in terms of thinking about why it is important, and then I will specifically, this is very important, introduce to you the commonly used terms for different types of diffusion. Because there is, as I said, a lot of confusion, and most of the general textbooks on materials science or materials physics do not distinguish properly. They distinguish maybe between the 2 basic types, interstitial diffusion and substitutional diffusion. But then when we especially think about substitutional diffusion, they do not differentiate often more according to the different types of diffusivities, different types of diffusivities for a uniform homogeneous material, let's say the big single crystal that we would always have in mind as an ideal concept. But then even more importantly, if we think of real materials, also including all the defects that are possible and that we always find, especially in metallic materials. And there also the different diffusivities even have different types of diffusion kinetics. And so we need to basically figure out a mathematical description, but also a conceptual description of each and every diffusion process. Because when we do diffusion measurements, it's a macroscopic measurement, right? And so if we have all these different types of diffusion processes occurring in a material, what we get out from the experiment is a net result, an effective result. And now we have to apply our brain in order to figure out how to get the information we like. So maybe we want to understand how fast is the diffusion really occurring only along the dislocations, or only along the grain boundary network, or in the volume. But if you get a convoluted product of all and everything going on in the material, this is not so easy. And this is what we will do or introduce today, especially concerning the different types and descriptions, because we cannot go fully to the diffusion fundamentals, as I said, because this would be an independent lecture. And the mathematical description applied to what is important for the materials we want to discuss, the higher entropy materials, I will introduce later when we actually have a look at real diffusion profiles. Because then I think it's conceptually more clear how to apply the mathematics in order to analyze the experimental results which you directly get from the lab in order to make out something meaningful from the data. So coming back to radio tracer diffusion, this is the mental image, right? So we would have a single crystalline block of one element, let it be pure gold. And we now want to measure how quick do gold atoms diffuse inside of this crystal lattice. And obviously there is no way we can, without any marker, right? Because there is no distinction between the atoms. And also there is no method we have to watch individual atomic jumps. So even if you go to TEM, even if you go to AFM, STM or so, you will not see individual atoms jumping. That's because of the aberrations of all the methods have, and also especially in TEM, you have always a projection view. So even if you make a very thin foil, you will basically collect the information on a 2D detector that contains all the information of the interaction of the electron wave, which you use incidentally, through the thickness of the foil. The thickness of the foil, even if you make the thinnest foil, will be several tens or hundreds of atoms. And so all the interactions between the interatomic interaction potentials, mostly the valence electrons and the electron wave, will give you the image. And so single atom hopping, no way, right? Too much convolution from all the other interactions along the beam path through the sample.
But in a single direction it can be.
You see?
In a single direction, like if I not depth I did not consider, then in imaging STEM.
Yeah, but still you get the convolution also along all the foil thickness. So you will not see an individual jump even if it goes only the XY plane, right?
So then what about APT?
Atom probe tomography also is not good because unfortunately the resolution in Z is perfect. You know, it's on the picometer level, so you can really decide on which terrace an atom was sitting before it was basically evaporated by the field. In X and Y, it's delocalized because you have these multi-channel plates, which basically give you the opportunity to do the 3D reconstruction, but half of the atoms hit these grids. So they are not counted. So the counting efficiency in 3D atom probe tomography is about 50% of the atoms only. This gives you a delocalization of the 3D reconstruction in XY, which is basically of the order of at least one lattice plane. So it means that even though you see all these nice images, they again have to be taken by a grain of salt, because only in Z it's accurate, in X and Y it's not accurate. Yeah. And so it means, again, no diffusive jump can be seen. If you go on a surface, like you have a perfect 1-1-1 surface on a crystal, no adsorbed layer, you do low temperature UHV STM. So it means that you basically look at the tunneling currents between a tip, which has a single atom as the lowest part of the tip, and you scan across the surface, and then you basically look at the interatomic interaction potential. You might actually see then a single atom movement on the surface. But it mostly takes place because you move the tip, because there is an interaction potential between your tip and the surface, otherwise you couldn't image it. And then when you move the tip, you kind of drag the atom. And it has been shown very nicely that you can pull single atom chains out of the surface of a material by STM, especially on gold. So you really get these singular chains of single gold atoms. And then actually I just saw 2 months ago a very fascinating result from this, where a person basically had an STM tip attached to a thin foil TEM sample. And so he was basically using the electron beam in this direction and the tip in this direction. So he pulled out a single atom chain, and he could image the single atoms in the chain by TEM. So fascinating. This is possible today. But if you want to go in the material and know something about individual jumps, no method will give you, unfortunately, any clue. So there's just macroscopically averaging methods which you can use, and then you have to infer from the convoluted signal of everything that goes on in the sample to the individual process. Yeah, so this is then the picture which we have, right? I mean, we have this, let's say, single crystal, which is homogeneous. In terms of chemistry, microstructures, defect distribution, everything. So an idealized experiment. And then we apply here the same element, but a different isotope. It could be radioactive, it could not be radioactive. Why would I want to use a radioactive material? You know, like handling radioactivity is not something which one does so easily. We do it in my laboratory, but could you think of a reason why we go through all the pain in having to fulfill all the administrative stuff and training students for a long time until they are allowed to touch any open radioactivity, because we want to prevent that anybody is contaminating his body? So why do we use radio tracers? Why do we not use an isotope which is not radioactive? You know, what do I do? This is showing you how the tracer experiment works, right? So this is at t equals 0. So I just applied my tracer. Let's say it's now just tracer, and I didn't tell you so far if it's radioactive or if it's not a radioactive tracer. So it could be a stable isotope or it could be an unstable isotope which decays, as you rightly said. Now, after applying a temperature and some time later, these marked atoms have diffused into my single crystalline volume, right? So what do I do now in order to measure the diffusion coefficient? Because this is what I want to measure. For this specific annealing temperature and also annealing time, I want to know how is the diffusion coefficient. What's the kinetic coefficient for the atoms diffusing into the single crystal? And the atoms are the same type of atom as the crystal is made out of. So what I do then is I interrupt so it means I quench the sample. I go down to room temperature. Means I'm going to a temperature which is much less than half the melting temperature. So efficiently, effectively, I freeze diffusion. So atoms are staying in place. There is maybe one or two or a few atomic jumps, but I don't care because I'm doing a macroscopically averaging measurement. What is next? Next, I section the sample. Right? So I cut it in thin slices. And then I take each individual slice, and now I have to count the number of marked atoms, of isotopes in each layer. How do I do that? How do you count atoms? Any idea? What method? If I would tell you I have the infinitely large laboratory, all methods you can think of are available, and you now have half a year to count the atoms in each section layer. Which methods could you imagine using? Yes, because you maybe cut it out with atomically sharp knife. So you label it section 1, section 2, section 3. And you have it on different plates, because the diameter of the single crystal would be huge, right? It would be millimeters, so it's easy to handle, easy to distinguish. But then you have to get the number of marked atoms in each section. How to do that? You could do any type of spectroscopy, mass spectroscopy. 3D atom probe is very similar to that, right? So you basically put this in a state where individual atoms are registered in a spectrometer, and an isotope has a different mass as compared to the original atom. This is why it's an isotope. It has a different number of neutrons in the core. And so you can distinguish with a mass spectrometer different types of atoms. This is one way. But this is only the way we use if there is a stable isotope, because the counting efficiency is horrible. So we get a very low sensitivity for measuring diffusion or for measuring marked atoms inside each section layer if we use this method. Much better is to have employ detectors which are able to register the radioactive decay products. So if you have a radioisotope, it will also migrate into the depth of your sample. It will be in the section, but it has a certain half-life, meaning that some of these atoms which are radioactive, which are unstable isotopes, will decay. And upon decaying, they give off radiation. And it could be alpha, beta, or gamma radiation, or sometimes you get more than one type of radiation given off, depending on the actual decay process that is taking place. And the detectors which you can use for gamma or beta decays are very, very much more sensitive than any method that relies on counting atoms. So the sensitivity contrast is of the order of 10 to the 4 to 10 to the 5. So you can measure quantitatively concentrations of radioactively marked atoms to 10 to the 4 to 10 to the 5 lower concentrations as compared to any mass spectrometry. And this is the reason why people use radio tracer diffusion, just because you can measure much more accurately and with much less concentrations of these marked atoms inside of your material. So it means that if the diffusion process is very slow, or if you have only very small number of diffusion channels in your material, still the radio tracer method can give you a result. For example, we are able to measure grain boundary diffusion in a bicrystal. Means you have a huge crystal, two bound together, and there's only one interface. So only one interface plane in an area of, let's say, a square inch. So it's not a large number of atoms to count, right? So no other method could do it, but with radio tracer diffusion, this is basically going to the limit of what the method can do with the detectors that are available today. This is the reason. Another reason is if we now add different atoms inside of a system, and also isotopes are different because the mass is different, right? If you add too high concentrations, you could change the local structure. So the diffusivity might be affected by adding these atoms into the structure. And then you'd get a result which is not really relevant for the pure material without these isotopes in high concentration. And this is why we like to have concentrations on the ppm level of these radio tracers. And only then we say that what we measure is really a signal that can be evaluated as related directly to the self-diffusion coefficient in a material of a certain element. So it's really two advantages. First, it's the high efficiency for detecting decay products. This gives you sensitivity. And coupled with this, the possibility to work with very low concentrations. Of marked atoms. So these are the two main advantages. Still, when we think about it conceptually, the atoms which we apply must be different. Otherwise, we have no way of detecting the diffusion. So even though they are the same element in terms of their electron configuration, the number of neutrons in the core will be different. And that means there will be a mixing entropy term. And there will be a very small but a finite driving force based on the concentration gradient, because we have a high concentration of these marked atoms here, and basically low concentration or zero concentration, depending in the crystalline bulk before the diffusion starts, and then we get the concentration profile. So it means we can apply the same mental picture as we had before. Right, so we have now something which after a certain time will look like this. It could be nonlinear, but let's say for the simplest case, single crystal, no other effects, we would have a diffusion profile which is nice and linear. And the concept now to describe diffusion is, again, we have here just a virtual plane. And we ask how large is the effective flux that we measure, and then we can again apply fixed diffusion equations by treating it as if we would have a concentration difference of a different type of element, and then you have the driving force, the chemical potential gradient, driving the diffusion of this species into the material. So we really use this kind of simplistic approach, but we have to keep in mind that it's on the brink of usability because of the fact that we have this very small difference of these marked atoms with the base atoms of the crystal. When we do diffusion measurements, we have to think about how to do them and prepare the conditions. But on the other hand, also the processes occurring in reality in applications are often governed by diffusion, but the diffusion process itself is affected by the process we use this material for. So for example, if you have an electric wire where you pass electricity through it, so you apply a potential gradient of the electrical potential, voltage, and that drives electrons from one side to the other side. Right? Do you know about the skin effect? Skin effect means that basically when you have a metallic body and you now apply a potential difference and you have charge carriers, the electrons going from left to right, basically because of internal screening of the because of the Fermi sphere or the Fermi hypersurface of a metal, it drives the electrons out of the volume of the metallic material and into a certain skin of a certain depth. And that is dictated by the properties of the metal. So it means when you apply a high voltage, many electrons will go through the material, but they will be concentrated in a very thin shell. So you have to take into account that whenever you either go to very thin wires, like in microelectronics industry, or when you go to high power applications where you apply huge voltages and have huge currents, that the electron density in the flux of electrons is very high, even just because of the skin effect. And so now you have all these electrons flowing in one direction, but the skin, this where they are flowing, is still part of the crystal, right? It's still part of the metal. We have
Basically, it follows the properties of the metal.
Yes, because the conductivity of the metal will be related to electron configuration. And this will dictate how much loss Joule heating, for example, is there. But let's say it's a normal metal. Again, let's take gold. Is it the best metal? Does it have the lowest resistivity, highest conductivity, or is there a better one? There can be better ones. Do you know an example? Huh? Yeah, maybe louder. Which pure metal has the highest conductivity? Is it gold? Because in microelectronics, connections are normally made of gold. Silver is also good, but not as good as gold. No, it's actually having high resistivity. Aluminum. Why do we not take aluminum? Because of the oxidation. So this is really a very huge stopper for the electrons, because aluminum oxide has zero conductivity. It's almost the best insulator, and you cannot prevent in industrial processing an oxide shell forming. So this is why we take gold, second best. So we have now a thin wire, right? We pass the current through, and it goes maybe from one part of this microchip to the external world to provide the power to run the chip. All these electrons pass through the lattice. What could they do in terms of atoms? Are they interacting with the atomic cores or not? Have you heard about nonlinear interactions, electron-phonon coupling? Basic physics course. Okay, so it's basically that you have interactions between the electronic system and the atomic systems. They are normally called electron-phonon coupling, because the electron wave can basically push atoms out of their position, really the core of the atoms. And so it means that kinetic energy of the electrons is transferred to the atomic system. So it means this is a diffusion process, right? Because the electrons kick the atoms out of place. And this is actually one of the mechanisms for failure. Maybe I put my glasses on, I forgot. It also happens in semiconductors, yes.
How electron will get this atom, because the nucleus and proton are the nucleus and the proton, they are heavily bound together and their mass.
Yeah, they push, I mean, they push basically onto the valence electron shell, and that gives basically a net pressure that, if it's strong enough, can really put the whole atom out of its. No, it's not always the case, but it depends on the push, on the current density, on the duration, and
There are various factors that it depends on. There are a number of factors that it depends on.
yes, it depends on the number of factors how strong the effect is, but it will occur in any case. And you see the outcome when you look at this wire. You know, this is a wire which was initially very smooth, and then you see what is called hillock formation. This is a technical term from electron industry, because this is a failure mechanism. You push atoms, and then they basically move along with the electron wind, they call it, so the flow of electrons. And at some point, maybe there was a small crack or there was a small, whatever, imperfection in the wire, and there they segregate, they aggregate, so they grow a new crystal, they find a new position, and this is then often causing mechanical instability, or maybe because of the electrical field and instability, so you can get a shortage with neighboring wires or so. So this hillock formation is something which is a very strong failure mechanism in electronics industries. And it's unpreventable because it's a diffusion process. I put this in parentheses because this is an example of a diffusion process which is kind of forced. So here the diffusivity will not be affected only by temperature and the material, but by the electron wind, right? So the more the potential difference is, the higher will be the flow rate of these atoms due to the electron wind.
They accumulate on
Yes, yeah, and downstream. Yeah, and that means they are missing somewhere. So you're thinning the wire at some end, and you're thickening and making these hillocks on the other end. And that once the wire is thinner, you get higher resistivity. The heating is more, which makes the diffusion even faster. So it's a kind of self-propagating failure mechanism. It gets worse and worse and worse very quickly. There is other effects.
Any steps to rectify?
To rectify, yes, people try to use coatings to get as little imperfections as possible, so that at least the distribution of atoms is rather even. But the general mechanism cannot be beaten, unfortunately. Yeah. Again, diffusion processes are very important also when you, for example, make interconnects. If you think of, again, electronics industries, flip chip or wire bonding is used. Again, do you know how wire bonding works? So it's basically you put the wire onto the substrate of where you want to bond, and then you pass a high current. And then there will be local heating because the interface is imperfect. There's a lot of Joule heating at first. So it means diffusion is created at this interconnect. And then you get diffusion bonding. So diffusion bonding, the term is very well known. It's also very important to do quick bonding on a chip, for example, of the gold wires. It's typically done not by soldering or anything like that, but by this wire bonding. So you tip the wire and it goes, the current flows as soon as the interaction distance is small enough, and then automatically it's heated up in the right position and it will do the bonding. What you might get is something like this, a product layer. This could be the interconnecting bonding layer, and then you are good and fine. But you're bonding different metals, right? Maybe a gold wire onto an aluminum plate. Well, you might get some phase formation at the interface between the wire material gold and the plate material aluminum. And so this is then what is called reactive diffusion. Because the diffusion itself causes a phase to form, which would now affect the further diffusion behavior, because the material transferred by diffusion in this product layer is different as compared to the wire or the plate which have been connected. And this is then making the mathematical description of diffusion even more interesting, because the partial differential equation system gets larger and you have to solve it simultaneously. So this is why in all these industrial processes, diffusion is really the key process. And actually, industry doesn't know much about it. So we have several projects with companies who, for example, are engaged in making these big wind turbines, and their huge DC currents they are created, they need to be converted into AC and to feed it into the network. And these huge current densities which occur there really require thinking about the diffusion processes, especially under the electron wind effects. And yeah, this is very active research going on. So from this short description, you already, I think, grasped that there is many different terms, right? Radio tracer diffusion, self-diffusion, reactive diffusion, and so on. So let's take a step back. First, I think it's important that we classify distinct types of diffusion. We yesterday already talked about it, and these are, I think, this is the very basic distinction. So you have obviously on the left side an interstitial atom in the interstitial lattice site. It stays in the interstitial lattice site, and then we call it interstitial diffusion. And if we have one of the atoms which consist or make up the lattice going from one lattice position to the other, then it's called substitutional. Diffusion. We will could there be a mixed type? Yes, definitely. An interstitial atom could decide to go on a substitutional lattice site and vice versa. Vice versa, you would find mostly under irradiation conditions, like in a reactor, because then an atom could be knocked out from its position, pushed into the interstitial lattice, so you have then an interstitial vacancy pair, and they could then again react, meaning change over time, either that the atom moves back to the normal lattice site, or it could also move in the interstitial lattice sites. These are the two basic mechanisms. There is one additional one, interstitiality diffusion. This is basically describing diffusion when an interstitial atom and a vacancy have such a strong bonding that they basically diffuse together. So the probability of them doing coordinated jumps is high. And then the mathematical description again is different, because a vacancy can more easily jump than any atom, whether it's in the interstitial lattice or whether it's substitutional. And so then this is kind of a coupled diffusion process. It's not very important for metallic materials, but if you think of semiconductors, then this is a mechanism which needs to be taken into account. We will mostly deal with substitutional diffusion, because we will be discussing higher entropy alloys, and we will not talk much about putting, for example, carbon into these materials. So for these materials and the type of diffusion processes, also related to whether there is sluggish diffusion or not, this is the type of diffusion mechanism we are focusing on. Okay, so obviously for substitutional diffusion, vacancies are necessary. And yesterday I already tried to introduce that jumps are not occurring very easily, because of the fact that when we think of how the elementary cell is filled in densely packed metals, like most of the high entropy systems, that there is not an easy way to go from one position where the atom is now situated to the next one that may be vacant, because a vacancy, a quasi-particle, is situated there, since all the other atoms, meaning the electron clouds surrounding the atoms, are kind of in the way. And so in addition to this 1 out of 10 to the 13 oscillations, which has enough energy to carry the atom from one position to the other, it needs also to push the atoms that are in the way out of the way in order to make the diffusive jump successful. And this is what is called transition state theory, which is the basis of all the descriptions of diffusion kinetics. And transition state theory is used whenever you have an energy barrier that is large compared to kBT. So Why does it need to be large compared to KBT? KBT means the thermal energy your system has under the conditions you're working, at the temperature you're working with, or you allowing it to diffuse, right? If an energy barrier for any process is small compared to KBT, the statistics of describing any type of reaction occurring means that you are in the fluctuation regime, meaning that the reaction can take place any time. Any oscillation, any excursion of the system might actually go to the new state. In this case, diffusion, it means the hop, the jump can take place. If the energy barrier is sufficiently high, then the normal motion will not be sufficient to overcome, because KBT is not enough on average to go above the barrier. That means you have to have a rare excursion, a rare event. And in statistics, rare event theory, rare event statistics are used to describe these processes. For example, Poisson statistics is one which is typical for these type of processes. So you have many 10 to the 13 that are unsuccessful, and then one is successful. And that lifts the atom above the barrier into the new position. And that is basically underlying the description of many, many processes. If you think now of temperature dependencies of these rates, let's say going from one position to the other, which type of law would you expect to describe the rate, the temperature dependence of the rate parameter? There's a very famous law. Arrhenius? Yes, very good. Yes, so it's the Arrhenius representation, goes back to rare event statistics and transition state theory for processes which are dictated or limited by activation barriers that are large with respect or in comparison to K Boltzmann times temperature. So all these processes, I hope I'm correct, but all the processes I know that follow this statistics can be described by Arrhenius law in terms of activation, right? So when we think of this substitutional diffusion, yeah, as I said, the presence of vacancies is important, or I would say it's vital for substitutional diffusion. There is actually diffusion processes which are described without a vacancy. And that's basically something like which is discussed also in terms, especially for semiconductor materials, for example, ring exchange. Let's say you have 4 atoms situated close to each other. One could move if the other moves, if the other moves, if the other moves. Since they are all the same atoms, it's still a diffusion process, but you don't get a net flux. Right, so I'm talking here about net flux processes and metals, so you need vacancies for substitutional diffusion. But, big but, there is always some vacancies present, right? This is again dictated by thermodynamics because of the mixing entropy between quasi-particles and particles. But you need often to have more than the equilibrium concentration of vacancies in order to have enough sites for substitutional diffusion. And so vacancies need to be created, and they need to be created where they are needed. And so if an atom wants to substitutionally diffuse in the lattice from one side to the next side, it needs to overcome the barrier between the neighboring atoms, and it needs to have a vacancy there that needs to be created. And to create a vacancy, also activation is necessary. So it means there are 2 terms for substitutional diffusion that are activated: creation of the vacancies, as well as doing the jump. And for interstitial diffusion, there is no vacancy necessary. So it means only the jump has an activation barrier, but not the creation of a vehicle for diffusion. So it means that interstitial diffusion is faster, activation barrier is lower in all these cases. This is very important. In reality, we have no single crystals, and even single crystals have some defects. And we have to worry about them because, as I said again, we do a macroscopic measurement. So it means when we measure diffusion flux, it comes from all kinds of sources, whether diffusion is occurring in the volume, but it also could occur in a grain boundary along a dislocation core, and this needs to be taken into account. Now, just to make this clear, what I have drawn here is an energy landscape. So it means the potential energy of a certain configuration of a material. So I might be here because I have annealed my material for a sufficiently long time. This means it's now in one configuration, meaning that atoms are situated on specific sites and defects are situated on specific sites, and somehow they have found a local minimum. This is why I am in equilibrium, but I'm not in total equilibrium, but in metastable equilibrium, right? Because this minimum is not the lowest minimum, it's just the local but not the global minimum. Now, if the system or nature always wants to minimize energy or free enthalpy in the case when we think of our systems, so it wants to go there. But how can it do? It can only do so by going the hard way. So the trajectory in an energy landscape cannot change the energy landscape. So it means it needs to go through hills and valleys to maxima and minima. And we have now two important. They are both local minimas because I didn't show you how the energy landscape would continue. But if I say this is the entire energy landscape, then this would be the right one here, would be the global minimum. So let's say this, for the sake of simplicity, this would be stable equilibrium, meaning that once the system has reached there, it will not longer change unless I apply an external force or field. If I now compare the potential energies of the metastable and the stable equilibrium, then I get a potential energy difference. What how do you call this in terms of activated processes? This is the net driving force. Because the term driving force means, I mean, the term is technically incorrect because it's not a force, it's an energy difference. This comes from the description of non-equilibrium thermodynamics, where forces and fields are affecting the direction of a thermodynamic system to develop from non-equilibrium towards more close to equilibrium conditions. But people have adopted this so that it's called the driving force. So the system wants to gain energy, and this is why it is developing in a certain direction. And this delta E here is exactly what is driving the system to go from metastable to stable equilibrium. So this drives diffusion, right? So in the end, the system can lower its energy. But there is also another very important energy difference. And this is the activation barrier. This is this term which is larger than KBT if we have thermally activated processes which are described by transition state theory. Where now is the transition state? If we now think of this process, right, that the atom needs to push through the neighboring atoms to go from one side to the other. Exactly. The most energetically unfavorable position is the transition state. Once it has reached there, it goes downhill, either going back or going forward. And the activation barrier consists of two terms. The vacancy pushing through the other atoms, but also generating the vacancy in the place where it needs to be. So this is the mental picture. Now, if I apply now a current, so we had this example, right, of the hillock formation along an electrical wire. So there is a potential difference which I apply to the material. Does it change an energy landscape? It does. You basically turn it. Any gradient of a field will basically turn your energy landscape. So it means also that maxima can become saddle points. Right? So it means that the diffusion process will be eased because it's more going downhill if you apply, in this case, the electrical potential gradient to the system. So this is very important when you see in the papers these potential energy landscapes. Often they are just a crude picture of what people think might be happening, but they often don't realize that whenever you have a directionality in the process, like applying any type of field, that you basically have to consider that the energy landscape is changed and that you, with the gradient, basically turn and shift the landscape so that the any processes go downhill more easy. So you change the activation barrier heights.
Activation barrier is same. Activation barrier remains same, right? The energy required for activation is same.
Yeah.
So
I mean,
same harder force.
the probability is different because it will be something like this. So you would basically keep the same. I drew it in the wrong way. So the delta E pot will be the same, but the barrier height will be less. Right? Because, yeah.
Is there any mathematical function by which, so that we don't have to plot it for each case? Is there any mathematical equation that we
If you have an equation to describe the energy landscape, yes, then you can just apply the gradient of the field.
minimize this, find the local optimum, then we can calculate whatever we need?
Exactly, yeah. But in reality, these energy landscapes would look much more complicated than a double well potential. Right, yeah. but yeah, if you have a function to describe this, then it's easy.
Use the computational models.
Absolutely, this is what's done. Yes, yeah, exactly, yeah. Welcome. Then on top of all this, let's say we have now a cross section. And we have etched it. Many of you might have done this already. So you polish very nicely and then you etch. So what do you see? Grain boundaries, very good. And so on. Do you see other things also? Dislocations, yes. So you get maybe small edge pits. Maybe you get precipitations. Now, when we So you get all kinds of defects, deviations from the single crystal. So if you go a step back, you don't do the etching, but you just polish. It's still there, right? All the defects are there. If we now mentally take this cross-section and turn it into the image which we have seen here, So the cross-section would be on this left side, right? And then we think about now applying our tracer, our marked atoms, and then let them diffuse. Difficult situation, right? Because we have to take into account that the tracer moves along the boundaries, but also along the dislocations, maybe along all the interfaces to the precipitate. It has a different rate through the precipitate as through the volume. So we have a diffusion coefficient for the grain boundaries, a diffusion coefficient for the dislocation cores, a diffusion coefficient for the precipitates, a diffusion coefficient for the interface, between precipitate and matrix, and we have a volume diffusion coefficient through the matrix. We also, if we are not careful, have a diffusion coefficient for the external surface, because we apply it on a surface so it can go around, right? It can trick us and fool us. And this is why we have to really do a lot of math in order to evaluate the diffusion profiles, because all of this might be occurring simultaneously. This makes it so interesting to do diffusion experiments. Do you have an idea which of the process is slowest and which is fastest? Grain boundary, grain boundary. Who is for grain boundary is the fastest? All of you? Or is you have a different opinion? I can tell you the grain boundary diffusion is not the fastest. So you can be confident in saying, no, it's not true. No, it's the second fastest. The fastest actually is diffusion along the free surface. So this is the fastest process. Excuse me? Yeah, this is now a good question, and a question I couldn't answer because it could be that diffusion in the volume of the precipitate could be faster or slower than the diffusion in the volume in the matrix. But all volume diffusion processes are always the slowest compared to grain boundary diffusion, compared to dislocation diffusion, compared to diffusion along an interface between two different phases, compared also to surface diffusion. So this one are volume diffusion processes. Yeah, and which one of the two would be slower? This is something which depends on the situation. What's the crystal structure of the precipitate? What's the crystal structure of the matrix? Would you have an easy concept to explain this hierarchy in diffusivities, in diffusion speeds, between in the volume slowest, on the free surface the fastest? Yeah, exactly. And one important point which you mentioned, which is the easiest concept to get a mental picture of why different processes have different activation energy. It's the excess volume. Yeah, so if we have in a structure like a dislocation core, more excess volume as compared to the surrounding ideal crystal lattice, then there is more possibilities to accommodate this atom moving from place to place. So it means the diffusion coefficient will be higher, the activation barrier will be lower. The same with grain boundaries and to the max on the free surface, because by definition on the free surface there are no other atoms on top of it. So the atom that wants to diffuse doesn't need to push them away. It can immediately hop into the new position. And this is why This is a very nice mental picture, and actually one can show by computer simulations, there was just a paper last year, that this can actually be done in a quantitative way. So you can derive a model, computer model for diffusion in grain boundaries, which is just parameterized by the excess volume present in a specific grain boundary. So it's a mental picture that is really rather accurate, which many mental pictures are not. And the same is true for dislocation diffusion. When we talk about dislocation diffusion, we call it pipe diffusion, because dislocation diffusion could also be misunderstood by how the dislocation migrates. But here it's meant how single atoms diffuse along the dislocation core. Since the dislocation core is thought of, and I think many experiments have verified, like a pipe. It has a distorted region which has a radius of about lattice constant or so, where the excess volume would be higher. So diffusion is then taking place preferentially along the dislocation core. There is one aspect one needs to consider here, and we will not talk about dislocation pipe diffusion much in this lecture. Be careful. Dislocation pipe or dislocation, the radius of a dislocation line is about the same order of magnitude as the atomic diameter. So it's bigger, but it's not much bigger. So if we now think of the description of diffusion as being based on Brownian motion, on random jumps in all directions that are possible, it's not the case here, right? Because the forward jump or backward jump along the dislocation pipe will be easier than outside, because there is higher density, less available spaces for doing the diffusive jump. And this is causing so-called ballistic effects, because the configuration space of possible jumps is confined in a one-dimensional way. And then the mathematics again change a bit. On the properties of the material, certainly, because you, for example, get preferential segregation of several of the atoms along dislocation pipes, and then you get something like these effects where you have dislocation motion prevented first by the segregating atoms, and only if a certain critical stress is overcome, then the dislocation can basically move away from the cloud of solvent atoms, of impurity atoms, and then sometimes they move again to the new position of the dislocation. So you have this, what is called Portevin-Le Chatelier effect, PLC, which gives you these serrated flow curves in mechanical testing. This is the reason. Yeah, and then it's important that when we talk just about the diffusion, for example, along dislocation cores or also in grain boundaries, we always have to think of the possibility of having both interstitial as well as substitutional diffusion that could take place. It just depends on the specific combination of which atom diffuses in which lattice, whether it's one or the other mechanism. Obviously, this is also cause of segregation. Right? Did I want to show here something? No, I don't think so. Yeah, if we go to the next type of defect, then we go to grain boundaries. So from 1D, dislocations to 2D grain boundaries, again 2D representation. And again, the same argument holds, right? So if we have atoms situated in a grain boundary, then very often that grain boundary has an excess volume. So it means there is more options to accommodate jumps of an atom. The activation barriers will be lower. If you should now venture a guess thinking about different grain boundaries, and I think all of you know that there are different types of grain boundaries, what would you think? Which grain boundary types show rather fast and which grain boundary types show rather low diffusivities? Yes, they are fast or slow? Fast. Very good. Yes, exactly correct. And then the low angle grain boundaries are rather slow diffusing pathways. What about special boundaries? I'm talking about CSL boundaries. This you know? You probably don't yet know? Okay. When you have, maybe I can even use it here. When we have boundaries, where we have a grain boundary plane defined like this, and we have two grains coming together, like green and blue. And you see when you follow one lattice plane up to the boundary, then the differently oriented lattice plane in the neighboring grain is directly connected. So there's a one-to-one connection between the lattice planes. And this is the situation where we have a specific CSL type lattice, so coincident site lattice of high symmetry, let's say. So you have many of the atomic positions in the grain boundary plane occupied by atoms that fit to both lattices. This occurs for different lattices at specific misorientations, so specific tilt angles or twist angles of the grain boundary, which means that we have a rather symmetric, well-ordered structure of these grain boundaries. And an example, for example, is a twin boundary. So you basically have then every lattice plane of one grain connecting into every lattice plane of the other grain. Then there is really no gain in excess volume or inside of the grain boundary plane, and then you will, or even though the grain boundary is a high angle grain boundary, but the specific diffusivity along that grain boundary plane will still be low. But these are specific exceptions. But normally, it's like your colleague said, high angle grain boundaries have much higher diffusivity. And it's again because of their more open structure. And in general, it also means that if you have a more higher misorientation between the grains, meaning if I put these two grains together like this, there is no misorientation, so it's not two grains, it's just one grain, because every lattice plane will be connecting. If I now basically do a tilt grain boundary, so I have a tilt axis here and I tilt them, the misorientation gets now larger and larger and larger. The larger the misorientation gets, the larger the diffusivity in general along this boundary plane, except for these highly symmetric positions where I again have this special CSL boundary like a twin boundary. That's the concept. And if we compare now for substitutional diffusion and surface diffusion, I already explained, there is no atom on the top, so it's very easy for the atoms to diffuse. Then we basically have in this Arrhenius representation, so meaning you plot the quantity diffusion coefficient as a function of 1 over the absolute temperature, and then basically from the slope of these lines you get the activation enthalpy. So it means that when we compare lattice diffusion, grain boundary diffusion, or surface diffusion, surface diffusion fastest, grain boundary diffusion in between, lattice diffusion the slowest, and the activation enthalpies the slopes. Are sorted in the same order. So it means on surface very quick, in the volume very slow, at the same given temperature. Yeah, I think I told you already all this. And again, interstitial, substitutional, both are happening basically along every defect. And now we come to how to measure it. And I said radio tracer diffusion, but I want to go back again to the diffusion couple, because this is what much more people are doing and can do, and even you can do in any laboratory where you have a scanning electron microscope and a furnace. You can do these interdiffusion measurements by using diffusion couples. So you don't need radioactive tracers, you don't need isotopes. Unfortunately, you can then not use the isotope counting, so you will lose sensitivity. But if you, may I ask you a question? Obviously, sensitivity is an issue, right? So you need to determine the number of atoms at a certain depth in your material after a certain time t at a certain temperature capital T. Now, if you have not a very good method, or maybe the resolution of your microscope is not so great, or maybe the diffusion process is just happening in a way that you find after examining your diffusion couple that you cannot really measure very accurately the profile, like how many A atoms have diffused into B and how many B atoms have diffused into A. Is there a solution for you guys? I mean, you cannot easily grab a new equipment into your lab, right? So you're bound by what you have. But how would you conceptually improve the situation? So let's say after 10 hours annealing at 500 Kelvin, you don't get a result with your SEM, your scanning electron microscope. What could you do? Raise the temperature, very good. So you go up in temperature, diffusion gets faster, so you do the same time, but higher temperature. And then at some certain temperature, you are bound to see something, right? Because it's a Arrhenius type process, meaning it gets much faster if you increase the temperature in a certain reasonable fraction. you could also wait longer at the same temperature, right? So diffusion experiments are nice because you can independently control the temperature at which the diffusion process takes place, and you can vary the time which you give the diffusion process to occur. Is this also providing help for distinguishing between the different diffusion processes that can occur? Let's say you have a polycrystalline high entropy alloy you want to, and you have two of them with different composition. You bring them together as shown here. They form a diffusion couple. And now you want to measure how nickel diffuses from one high entropy system into the other high entropy system. But you know there's grain boundaries. You know there are dislocations. You know that maybe one of the high entropy systems you bring together has also even a second phase. So from what I have told you so far, is there a way out? Can you distinguish? By planning the experiment in a systematic way. This might help you. Yeah, but let's say your diffusion zone, let's put it like this. In a scanning electron microscope, you can only, in cross-section maybe, get the average concentration of a certain element. So you can measure diffusion profiles. But the resolution by which you can do it is not sufficient to look at individual defects. So you will not see diffusion along a grain boundary. You will not see diffusion along a dislocation core. Why is this? Because there is an interaction volume between your incident electron beam and basically the X-ray radiation getting out by the electrons attenuating the atoms and knocking out electrons, so jumping back, giving characteristic X-ray radiation. And this comes from a volume of roughly 1 cubic micrometer. And so anything which is much smaller, you will not be able to resolve. But, you know, if you, for example, now, again, make the time shorter and shorter, what will you do? You will freeze out the slowest diffusion processes because they cannot contribute much in this shorter time to the diffusion, to the net overall diffusion flux, right? So the shorter the time at a certain temperature, the more dominant will be the outcome of all the diffusion processes on the measured profile of the fast processes. And if you don't have the free surface included, then it will be grain boundary diffusion. Or if you wait a little longer, maybe also dislocation pipe diffusion. And then you can also lower the temperature, play with temperature and time, so that you go to conditions where volume diffusion basically is not taking place because maybe it's only one interatomic distance the diffusion jumps can do in this time at this temperature. But if the grain boundary diffusion is 4 or 5 orders of magnitude faster, many of the jumps will occur, so you will get a diffusion profile, but only from the grain boundary diffusion part, from this past part. And this is the beauty of diffusion experiments. If you plan them in a systematic way, you can select ahead of time which type of diffusion you want to analyze. And this is how it's done in the experiment in reality. So you can deconvolute experimentally. You don't need to do all of this mathematically. There are just some processes which do not have such a large contrast, like for example, phase boundary diffusion and grain boundary diffusion will occur almost at the same diffusivity. So there is not really a window where you can select only one of those, then you have to do the proper math. So diffusion couples, important because also literature on diffusion in high entropy systems, the early ones, sluggish diffusion, were done exactly with this approach. And basically here it's sketched what is the main idea, right? So you bring together two dissimilar materials this time, and cross the original interface, diffusion fluxes occur of some constituents from the A side to the B side and some constituents from the B to the A side. Always there is vacancies now included in the picture because I'm talking about here substitutional diffusion, even though for interstitial diffusion the picture here would be the same. But if we consider now substitutional diffusion, would you expect that the fluxes of A into B and B into A are always equal? No, definitely not. Very good. Would you expect that this also affects the vacancy flux in both directions? Yes, perfect. I'm happy. So it means you have a net flux of vacancies from one side to the other, right? What does it mean for the microstructure? Void formation, thank you, yes. What's the name of this effect? Kirkendall effect, yes. So it means when you have dissimilar fluxes, you have void formation. And that's, again, something which is important for applications because you often have dissimilar joining in applications. And then if you have diffusion processes, Kirkendall voids are almost not to prevent. And that obviously is stress concentrator and failure mechanism. For diffusion and for the diffusion studies itself, this is important because sometimes one can use these Kirkendall voids as markers of the original plane where the materials have been joined. But that's another story. Here, just to introduce some terms which are often used, this is called an interdiffusion process, right? Because yeah, you have dissimilar materials, dissimilar components interdiffusing into each other. Sometimes you read in the textbooks also that this is called chemical diffusion. And people are using both terms, even though interdiffusion is the more general term for the situation present when you investigate a diffusion couple. If only if a new compound is formed, so if you have a reactive diffusion, new compound at the interface, then one would call it chemical diffusion coefficient. In fact, atoms A and B are diffusing across the interface, and that means we have to distinguish between the individual constituent diffusive fluxes, and they are diffusing with their intrinsic diffusion coefficients, and then the net flux coming out of the coupled A and B diffusion is then called the interdiffusion flux. So I know it's many terms, and it's basically often due to historic development that people have been using it. I don't think it's very consistent, but that's the way it is. So the interdiffusion flux is just the average of the two intrinsic diffusion fluxes. Then obviously the diffusion coefficients are also having these names, and the interdiffusion coefficient can be easily calculated based on the intrinsic diffusion coefficient. Right, so intrinsic is without this wave across the D, if the specific volumes of the two materials are rather equal. If they are very different, then one has to apply a correction term. I'm not sure, is it time to stop at the moment or? Okay, maybe just, let me see what the next slide has. Okay, yeah, I think this I already told you in the beginning. So self-diffusion obviously is something which would happen anytime. So if you have a pure piece of tin sitting on the table because you want to do maybe some soldering, be aware that there's a lot of self-diffusion going on at room temperature in this piece of tin. You will not see any of this because this is just an exchange in random orientations. So the distinction between tracer diffusion and self-diffusion is that we still have a concentration gradient in tracer diffusion, so we have a net flux. Self-diffusion by definition doesn't have a resulting flux. So this time I was not so going fast, but maybe it was still important. So let's go through this. I mean, I basically just said everything about tracer diffusion which I wanted to say. Just one important point, because again, in the literature, when you read it, people talk a lot about self-diffusion. And they use some of our data on tracer diffusion, and they often say it's the same. It's the same if it's interstitial diffusion, because there the interstitial lattice is symmetric about the position where the atom starts. It can go in any direction. So the correlation factor, meaning how the effective diffusion length after a certain n number of jumps compares to the random walk, is unity, because you have no preferential direction. There's no coupling with the lattice because the interstitial lattice is just there. If you have substitutional diffusion, there might be very different ways how the vacancy can interact on this lattice side or on this lattice side with the atom you are now observing. And this is called a correlation, causing a correlation factor, causing cross terms in the diffusion matrix. And so the correlation between random walk diffusion distance and real diffusion distance after n jumps for substitutional diffusions in real lattices will not be 1. And this difference, which is not 1, will be the so-called correlation factor. If you want to look into that, you look into the very basics, fundamentals of diffusion, because then people are applying so-called 5-frequency models. They were first invented by Manning, where basically there are, for FCC lattices at least, it was speculated that there are 5 principal frequencies by which vacancies can motion through the lattice. And these 5 principal frequencies are used to calculate principal correlation factors under different conditions. In reality, we measure basically and see what the correlation factor is, because otherwise you do basically a computational study. You cannot do it by hand analytically. But just to let you know, tracer diffusion coefficient and self-diffusion coefficients can be transferred rather easily into each other, but they are not the same if substitutional diffusion is taking place. And with this, I think I stop for today, taking questions if you have. But then on Friday, I will talk about grain boundary diffusion, which is a favorite topic in my lab, because we are the only lab in the world that can measure it. But maybe you have questions. Hopefully I will be back, and looking forward to see you then again. Thank you.